this is where you get performance.
I know. Some sort of magic trick. Oh. There we go. Okay, we'll get going. Like Joe said, I'll be talking about particle and cell simulations of plasma interaction with lunar crustal magnetic anomalies. This is work that's done as part of one of the NASA Lunar Science Institute teams, the DREAM team. Looking at, the team itself looks at the global interaction of volatiles and plasma and space weather with the moon. And here I'll be focusing mainly on magnetic anomalies. Okay. A little bit of introduction and scientific motivation. Why is it that we're focusing in on magnetic anomalies? Talk about the model itself. What is it we're trying to pick out? What small piece of physics? What are the limitations? Talk about the results. And also the conclusions and lots of ongoing and future work. Now, lunar magnetism. It's been known since the Apollo era, when it was discovered by one of the sub-satellites. Since then, we've had numerous missions, Lunar Prospector in the 90s, as well as Kaguya and later missions. What I'm showing here is a global map of the magnetic field magnitude, or strength at spacecraft altitudes, roughly 30 kilometers. And here you see the the near side and the far side. What you see is that the magnetism on the lunar surface is highly incoherent. It's highly scattered. It's highly non-dipolar. But there exist localized regions that are very strong. Now, in this color bar, the highest you get at altitude is about 18 nanotesla. But down at the surface, these magnetic field strengths can range up to hundreds of nanotesla. And one of the possible implications for this is solar wind shielding of the lunar surface and what types of interactions that the solar wind will undergo with these magnetic fields. So there's a variety of effects, like I said, that we believe are a result of interaction with these fields. One is the well-known lunar swirls. I show here a figure of the Reiner Gamma lunar swirl, overplotted with contours of the magnetic field strength. So there's an obvious degree of correlation between the surface albedo as well as the magnetic field strength contours itself. And this leads itself to the suggestion that somehow, via some electromagnetic process, these magnetic fields are shielding the surface from solar wind bombardment. We also see recent work by George Kramer. We see that the surface is actually also correlated between the albedo and the hydroxyl abundance in the surface, directly overlaid on the same pattern. So whatever mechanism is creating the change in the albedo of the surface is also directly related to whatever mechanism must also be causing this deficiency in the band depth of hydroxyl on the surface. Now, there has been previous modeling work from one aspect or another to look at how these mini magnetospheres may form. There's sort of mini global simulations in an MHD perspective that look at how sort of test dipoles buried under the surface can actually shield the solar wind. You get kind of a bow shock here where the density changes sharply, and this is thought to be able to shield the surface effectively. There's also been more recent results published by Chandrian that looked at a global map of reflected proton flux. And this proton flux correlated very well with the contours of lunar crustal magnetism. And this was not even from a global sense. You see there's a lot of field contour lines denoting the largest concentrations of fields. But you can even pick out smaller ones where there's relatively weak anomalies that actually have a high degree of reflected proton flux to them. So these pieces of research put together are really pointing towards a more coherent picture that these magnetic fields are able to somehow very efficiently reflect solar wind protons very close to the surface and prevent a lot of these various effects, space weathering included. Now, there's a recent publication by Kaguya, which in 2009 had a spacecraft flyby that flew through an anomaly interaction region. And what they noticed was a series of what they would call high-altitude electrostatics. So as the solar wind comes down these field lines, there's a magnetic anomaly buried in the surface. Kaguya flew at about 25 kilometers in altitude, and what they noticed was a static or a DC electric field sitting right above the anomaly region. And they were able to discern this because they saw simultaneously the electrons being accelerated into the anomaly and ions being decelerated at the same energy. And that's a classic hallmark of a static electric field. Now, the cartoon picture that you get from this is that the magnetized ions are reflected very efficiently by the magnetic mirror effect, The ions sort of lumber in a little bit more, and this sets up this charge separation, which leads to an electric field. However, many questions remain. Kaguya saw ion heating at the lunar surface. We don't know what's causing that. We don't know how the lunar surface itself is charged within this anomaly. We don't entirely know what the surface electric field is and how that feeds back ultimately on the solar wind proton flux. Those are really the answers, are the questions that we're trying to get answers to. Now, the modeling that I'm doing uses a particle and cell where we're tracking individual electrons and ions in this region. I show here a very cartoonized version of a magnetic dipole, and the results I'm showing here today are looking at the cusp region, so the region where you have open field lines into the solar wind. We have ions from the solar wind that kind of lumber right in. They're unmagnetized. We also have electrons shown in blue that are both magnetized and also feel the electrostatics. What we're looking is to discern what pieces of this electric field that you build up these field lines is due to this ambipolar field where you get charge separation, and also this sheath electric field where these charges are interacting with the surface themselves. This is a plot showing some of the model runs we did for the magnetic field strength as a function of height. So you have down here in the meter range up to about 10 or 25 kilometers. The colors simply denote a sort of a scale that we ran for different magnetic field strengths, running from about virtually no field, 1 nanotesla here, plus a background of 10 solar wind nanotesla field, all the way up to 10,000 nanotesla, which is actually far past what we would observe at the moon. The moon is known to have fields that are sort of in the hundreds up to about 300 nanotesla range. What we find, what I show here is the main output of the model shows the electric potential as a function of height above the surface of the moon. So here's 10, 100 meters, 1 kilometer, up to 25 kilometers. We see that as we increase the magnetic field strength, this electric potential builds up inside this cusp region. And this directly is the ambipolar field that Kaguya was measuring as they flew through here. However, they were flying up here at tens of kilometers, whereas the peak of this electrostatic field is way down, very deep in the anomaly at about 100 meters. And this is really where you begin to turn around these protons. At heights below this, heights below roughly about 100 meters, the electric field actually switches sign. And this is due to the fact that you have the lunar surface sitting right here, which charges up as some amount of electrons do reach the surface. What this is really pointing to is that this is a complex electrostatic field, even within this very simplified, somewhat idealized region of a magnetic cusp region. Now, how does this actually affect the particles itself? What I show here are phase spaces. They're simply individual ions. Their velocity is here on the y-axis. Their height above the lunar surface is here. This beam here is the solar wind beam itself. What you're seeing is that for very weak fields for 5 nanotesla or left, there's really no modification of the incident beam. It's directly impinging on the lunar surface. We go up in order of magnitude in magnetic field strength. We still don't see much effect at all. And really, you wouldn't be able to discern a difference between these two. What we do start to see is for strong enough fields, about 500 nanotesla, we see this very thin reflection region, and that is down in the hundreds of meters, less than a kilometer. And that is the electrostatic potential has built up high enough within this anomaly region to electrostatically reflect these protons. This thin stream is then reflected way back from the moon, but you also notice the incident beam is modified as well. There's a lot of turning up, there's a lot of phase-space dynamics, ion phase-space holes that lend to a lot of this heating, which is possibly what Kaguya was observing. Finally, take things a little bit farther. If we amp up the magnetic field another order of magnitude, we get to about 5,000 nanotesla. You correspondingly see much more reflection. Now, from those individual phase space plots, I can actually calculate the proton number flux and the proton energy flux to the lunar surface. And I show that here as a function of the magnetic field strength at the surface. So down at very weak fields, less than, say, even 100 nanotesla, this is the normalized proton flux from the solar wind. So a value of 1 is basically the entire flux you would get from an unshielded region. And what that's really pointing to is in these cusp regions, even though you're building up these electrostatic potentials, they're not strong enough to stop the solar winds in these very narrow cusp regions. We can sort of divide these very roughly. We get an unshielded cusp region and a partially shielded cusp region where you begin to see some drop-off in this proton flux to the lunar surface. Now, interestingly, I talked about the maximum field strengths that we see on the lunar surface, and if I highlight that here, 327 nanotesla corresponds to the highest known field strength at the lunar surface from the Apollo 16 surface magnetometer, and it almost by coincidence, sort of bisects this into the unshielded cusp region and the partially shielded cusp region, where for expected field strengths on the lunar surface, within their cusp regions, they're basically wide open to the solar wind. Finally, a quick comparison to that single Kaguya measurement that I pointed out earlier. What I show here on the left is the magnetic field strength contour map. So you can see it's about 30 degrees in longitude, 30 degrees in latitude. The crosshairs denote the point of Kaguya where they measured this electrostatic potential. It's over one of these medium strength anomalies, a couple hundred nanotesla. What I also show here on the right, the model is shown in black here. This is the ratio of the max electrostatic potential energy, so how strong of an electric field are you building up, versus the solar wind bulk energy, just 1/2 MV squared of the incoming solar wind. I can peg this to the magnetic field strength that was observed by Kaguya. We can put a lower limit and an upper limit. We don't actually know the exact value of the electrostatic potential that Kaguya measured it because it didn't measure at 100 meters above the surface. It flew over and kind of caught the tail of the potential. But even at a qualitative basis, the range of this model that's consistent with Kaguya shown here is gray, and our model slices right through that. We would predict a little bit lower, but nevertheless it's within this region of validity. So the spacecraft measurements are somewhat consistent with the model, and that they predict right about the strength you would expect for this electrostatic potential within these anomalies. Finally, we talked a lot about Artemis this morning. One shown here is a sample measurement that we've begun to collect. You can see here the magnetic field trace is quiet, and as we fly close to the moon, the magnetic field strength is perturbing the incoming solar wind magnetic field. You also see here in the proton spectra a lot of reflected fuzz coming off of the solar wind proton beam. Those are reflected protons similar to what Kaguya saw. So we're busy accumulating these measurements. They come somewhat infrequently from Artemis measurements because of our very elliptical orbits around the moon. We kind of have to get the right geometry and get a little bit lucky to fly through one of these. But these are really high-resolution spectra, both in energy, space, and time, and really will allow us to conduct a lot more comparison with the model. I'll leave this up here and take any questions.
It's time for one, and I saw Jack's hand first.
Andrew, Andrew?
Yeah.
If you can go back to one of your first slides that shows the magnetic field of the near side and far side of the moon, one thing that kind of jumped out at me, and maybe it was the projection. Yeah, that's good. The far side, you've got an amplification of the magnetic field in the southern hemisphere and the far side, but it doesn't look like it coincides precisely with the South Pole Aitken Basin. The South Pole Aitken Basin goes a little bit further.
Right.
Maybe it's just my eye, but is there any explanation for that morphology that you see in the magnetic field there?
So the morphology that's shown here, and actually if I zoom out to the big one, what it's showing here is actually the magnetic field at spacecraft altitude,
right.
So 25 kilometers. So since the fields are highly non-dipolar, they actually die off very quickly as a function of height. So admittedly, this plot is perhaps not the best with correlating with surface features. From there, you'd want something like the inferred lunar prospector map from electron reflectometry. There you do see a lot more features that correlate with topographic features. But I would hesitate to take something like this at spacecraft altitude and begin to infer any topological comparisons.
Okay, in order to stay on schedule for now tonight, we're going to have to move on, but thank you.